Carbon footprint analysis from web and phone calls. Hello, my name is Altnai Bisht, and this is my project presentation on the subject Big Data Analytics taught by Dr. Lin Li. Internet explosion has become an environmental problem. The footprint of web transactions, web calls, virtual meetings has been increasing, and these are some different stats reported by various research houses. So have you ever wondered what is the carbon footprint of your web conferencing call? There could be multiple parties, and multiple parties could be establishing peer-to-peer connections among themselves and with a media server, which in overall calculation leads to a very high carbon footprint. In this project, I analyzed the big data from these web calls to calculate the carbon footprint. I follow the ETL process and then calculate the carbon footprint. The first process, which is extraction of the call logs, recordings, and call records, will give us a format that we can process in our pipeline. The three data sources that I have used are unstructured call server logs, the structured call detail logs, and the media files from the call recordings. This is a snapshot of some of the call server logs. The call server does not follow any structure. As we could see in this snapshot, it is more like a dump of all the logs, network stats, and other debugging notifications from the server. The call detail records are more structured, like a CSV file, and follow specific columns for values such as call start time, call end time, call IDs, duration, etc. The most complicated aspect of the project is processing the call recordings, which are themselves MP4 files. For the purposes of my project, I am not reading the content of the log file, instead reading data from the metadata of the call file, such as the start time, the modified date, and the end time for these call recordings. Overall, I process the timestamp from these three data sources and calculate their frequency. We could see here on the screen the count for the rows that I've filtered from these various sources. As I transform my data to yield the structure that I need for my processing, I see that my data set is skewed towards the front side. As in, for few dates, the call volume has been showing is very high. And this is also depicted in the figure below. These are some snapshots from the Spark UI to show the loading and the RDD as well as the DAG cycles from my process. As I will demonstrate my aggregator, I would like to point out that the aggregator that I have developed can be used to do pattern analysis as well as real-time stats. Let's see the demo. This shows a runtime execution of my project, which starts with the three data sources, which is call records, the call logs, which are unstructured, where I use regex to parse for date timestamp. As you can see, most of the fields in the logs are empty, which I will filter later on. I also filter for a date between 2015 and 2022. The third source used is the audio files, where I'm reading the creation time as the metadata for my processing. I also filtered this dataset between my timestamp, which is 2015 and 2022. I then proceed to combine all of these three data sets, which are now in a similar format, to give an overall data set by using union operation from the RDDs. Due to the high volume of my dataset, the processing takes quite a while, and this is a fast-forwarded video. Let's try this again. And this is the first 20 rows of my overall data set. I then proceed to calculate a pattern analysis for a hour by hour usage of my call and a day by day usage of my call. The processing takes some time. I'm extensively using the Spark methods which the library provides to do my real-time analysis and pattern analysis. This graph shows an hour by hour analysis, and the upcoming graph shows the frequency. The data set is distributed in 15 minutes of interval. I have also extensively used the PySpark SQL functions for my processing. And I use plotting to show the distribution of my data set. As explained earlier, this data set is skewed at the front of the year, and hence the graph shows likewise. For my records, most of my logs show high call volume at the starting of this year, and my audio files show high call volume in the year 2015-2016. This will be reflected in the overall call traffic analysis in the yearly graph, which is shown here. So the call volume for 2020 exceeds 2015 and 16, which is not coming out clearly in this graph. For the purposes of carbon emission calculation, I use a Python library called Carbon Footprint Calculator, which is my self-published library in the Python package store, to calculate the fuel by fuel distribution of my VoIP calls. As shown in the graph generated, the carbon footprint of a VoIP call varies across a day, which is primarily driven by the kind of fuel which is powering our electricity grid at the moment, which for some parts of the day could be highly contributed by natural gas, and for the other parts of the day could be highly contributed by solar power, which fluctuates the carbon distribution throughout a day. And as also demonstrated in my worksheet, the fuel by fuel energy efficiency and a fuel by fuel carbon footprint can give us a good idea about the carbon footprint of our call. This is the graph that is applicable to Northwest, and this graph I generated for the California ISO region for the VoIP calls. The conclusion is that Spark has simplified the process of analysis from such rich and varied data. I am also able to extend my data pipeline architecture to other sources such as Spark Streams, HDFS stores, and other real-time data. The roadmap would involve doing this on a real-time voluminous data set, and I also seek to pursue and publish this work, or open source this work for others to gain. The findings from a segment of the data, which was real data, shows that the distribution of the call is towards the center of the day, and most of the voice calls correlate to a high increase in carbon footprint. So, which basically shows in this section, this is usually the peak hour in a day where the electricity consumption is highly driven by carbon-rich sources. So some calls may have a larger footprint than other calls as they are distributed across the day. These are some of the tools that I have used for my work. Some of the challenges and the use cases involved. The challenges are the timestamp related challenges, as there could be different time zones for different parties during a call. So we need to extract the location of all the participants in a call and take the electricity generation from their geographic region respectively. I also intend to add constraints for the for filtering based on the codecs, as some audio video codecs are more energy efficient than others, and also for the definition of the call, as mobile agents consume less carbon, rather emit less carbon than a high definition call, for example. The use cases can involve a carbon tax on VoIP calls, which could prevent spammers and call centers from making huge duration calls, as they would show a higher carbon footprint than a regular user. It is a novel concept, as I have not found any work which can use these kinds of sources to calculate carbon footprint from a VoIP call. And I also can use the same big data structure to also evaluate the carbon distribution from chats, from blank calls, from voice or video calls, as well as from multi-party or conference calls. And this project does not infringe on privacy or security. Thank you.